Hello students, welcome to physics class.
The angular momentum is similar to the linear momentum in translatory motion. A body in translatory motion has a linear momentum, while a body in rotatory motion has angular momentum. Angular momentum can be defined as the cross product of position vector and momentum vector. L bar is equal to R bar cross P bar, R bar cross M into V, whereas V is omega bar cross R bar. So the angular momentum finally is expressed as mr square omega. Here mr square is nothing but the moment of inertia. I is equal to mass times square of the distance between axis of rotation. Next, law of conservation of angular momentum. Angular momentum of a system remains constant only there is no external torque on the system. When there is no external torque, the total angular momentum of that system remains constant. When there is no external force acting on the system, then the linear momentum of that system remains constant. When only there is an external force, a linear momentum will change. When there is an external torque, the angular momentum will change. From the Newton's second law, torque tau is directly proportional to rate of change of linear momentum. If torque is 0, then the derivative dl by dt becomes 0. Here, when the derivative becomes 0, the derivative variable L is equal to constant. Next, L is equal to constant means we already know that L is equal to I omega, therefore I omega is equal to constant, which implies I is inversely proportional to omega. The law of conservation of angular momentum can be observed in some daily examples. First one is ice skating, and second one is a diver diving from a diving board. Next, a ballet dancer. These three are explained as when the person outstretch his legs and hands away from the body, then its axis of rotation is passing through its center of mass, and the distance from the axis of rotation is r. When the person holds his legs and hands towards his body, then the distance between the axis of rotation will decrease. Because the distance from the axis is directly proportional to moment of inertia, when the radius increases, moment of inertia also increases. When the radius decreases, moment of inertia also decreases. When the moment of inertia increases, angular velocity decreases. When the moment of inertia decreases, angular momentum increases. So, by holding the legs and hands towards his body, the person can increase his velocity, that is angular velocity, by outstretching his hands and legs away from the body, its angular velocity will decrease. In the same way, the earth orbiting around the sun. When the earth is orbiting around the sun, at perihelion and aphelion points, the angular velocity of earth here increases and here the angular velocity decreases. Here the reason is that at the perihelion point, the radius or the distance from the sun to earth is less, whereas at aphelion point the distance from the sun and earth increases. When the distance decreases, angular velocity also decreases, angular velocity increases in this case. When the distance increases, the moment of inertia increases, hence angular velocity decreases. In the same way, a vehicle can be balanced while moving than at rest, because the law of conservation of angular momentum holds good in this case, because there is no external torque acting on that bicycle. In the same way, the helicopter has two propellers. One is rotating from left to right and another is rotating from right to left. The torque developed by one propeller is cancelled out by the another. Hence, the angular momentum remains constant. A boiled egg and a raw egg can be distinguished by spinning them on the table. The raw egg spins slower than a boiled egg. That is, a raw egg comes to rest very soon as compared to a boiled egg, because the boiled egg has lower moment of inertia, hence its angular velocity is high. This is all about angular momentum and conservation of angular momentum and some examples related to the conservation of angular momentum. Thank you.